Well, thanks for coming today. We've got a good friend of mine, Ed Cohen, from Imperial College. He's a lecturer there in statistics, and a good colleague, somebody I've known for a long time. So I'm looking forward to hearing his talk, Spectral and Wavelet Coherence for Point Processes, a Tool for Cybersecurity. Thanks, Ed.
Thanks, Josh. Really lovely to be here, so thank you very much for the invite. So yeah, I'm looking forward to talking to you about some of the work I've been doing. So my background, I'm a colleague of Nick's, so I work in, if you were at Nick's talk yesterday or saw his talk, I work in the same department as him. And I don't come from a cyber background, and so the tools which I'm going to be showing you today, they have been developed independently of cybersecurity, mainly as a methodological pursuit in its own right. However, there are some interesting applications for this methodology, and I've highlighted cyber as being possibly one of them. So hopefully I kind of will give you a flavor of the kind of things which these tools can do in this setting. So a little bit of a motivation. I'm sure the first point there resonates with people here. The understanding and characterizing how devices on computer networks communicate is a challenging task. You know that these are huge, messy, complex data sets, and trying to find any kind of structure within these data sets is difficult. However, I think the second point here is quite an important point, that as network defenders, you should be at a theoretical advantage over the attackers. You can model and you can understand what normal day-to-day activity should look like on a network, and you should be able to exploit that fact to your benefit. Anyone looking to attack a network would have to somehow create a signal which you wouldn't be able to spot. And so with the huge data sets you have available to you of normal network activity, you should be able to have an advantage from that. And therefore what I'm kind of going to be talking about in this is, can we kind of form models for what normal network activity looks like, so that we can then define and spot anomalous and or malicious events. Okay, so in this talk I'm going to be focusing on the analysis of net flow. And what I'm going to be looking at is how we can detect and characterize correlation across edges of a network. So for example one, you may expect that net flow data between pairs of devices are not correlated in any way. And therefore, if your net flow is correlated across pairs, then this may indicate potentially malicious behavior such as lateral movement or tunneling. Or another example, you may expect some broad correlation in network between pairs of net flow between pairs of devices. E.g. some kind of self-exciting and mutually exciting behavior going on, and I'll touch on these ideas later in the talk. However, if suddenly you spot some unexpected periodic signal is present across these data streams, then this may also indicate malicious behavior of some kind. So what I've got here is what we'll be starting off with in this talk is that we have three devices, A, B, C. There is net flow from A to B and net flow from B to C. And we'll be looking at whether the net flow which is occurring on these edges between these devices is correlated, and whether we can understand anything about that correlation and the structure of the correlation. Okay, so if I formulate the problem, then we're going to start with a simple device triple, A, B, and C. Three devices, A, B, C. These might be personal computers, servers, authentication servers, printers, etc. And they're sending information over directed edges. And what we're going to be looking at is that, through packet transfer, which is summarized by net flow data. And so what we're going to be doing is we're going to be modeling the net flow, the start times of the net flow events as 2-point processes or event processes. And I'll come on to a little bit about what this notation means later in the talk, the NAB and the NBC. But that is a notation for point processes or event processes which are occurring on these edges. And these are our event processes which are modeling the net flow data. And our aim, or my aim, in this is that we're going to detect and characterize the correlation between these two event processes. Any questions at this point about the setup of the problem? Good. Okay. Okay, so maybe some traditional approaches to modeling network traffic is to assume that these are generated according to a Poisson point process. Poisson point processes can be generalized to multivariate setting. It's not particularly easy, but you can just put 2 point processes together and have a multivariate point process. But what point processes don't allow is for you to encode autocorrelation structure within the point process. Poisson processes, by definition, have zero autocorrelation structure. They have zero correlation in time with themselves. And so it's a restrictive model for this. And also, when considering computer network traffic, it's not hard to imagine that events from a device will somehow be dependent on previous events from that same device. So that would be, there would be some autocorrelation structure involved in this, okay? This might be some kind of self-exciting behavior, or even self-inhibiting behavior, self-exciting being, I'm sending some information to another device, and because I've just sent some information, I need to send some more information. Or self-inhibiting, I've just sent some information, I'm done for a while, that means I don't have to send any information now. That's positive and negative correlation built into the point process. So spectral approaches to characterizing this correlation are based either on Fourier or time-scale wavelet analysis of the random processes. And what they do is they provide a brilliant and very rich description of autocorrelation and cross-channel dependency. And they have done in a huge array of engineering disciplines, science disciplines. They are a kind of a standard way of, they have some really nice properties, which I'll show you later, of understanding correlation. But in a cyber setting, this is, in my opinion, yet to be explored. So what's going to be coming up in the rest of this talk is I'm going to propose that we can use spectral coherence to characterize correlation between network communication channels. Coherence hasn't been used in network traffic before. Well, it has now because I've just had a paper accepted at a conference. So now it has officially been used in modeling network traffic before. Now has officially been used for not modeling network traffic. One thing, though, it's been used a huge amount in neuroscience. And I think the cyber community could find a lot of interesting work in neuroscience and neural engineering. In neuroscience, it's used because you have neurons which are firing events. So neurons will fire, and that will send an event. That firing is an event, in the same way that computers are. You can model the information they're sending as events in time. And these spectral methods have been used a lot in neuroscience. And so I think there's a lot of interesting stuff in the neuroscience literature which cyber people could benefit from looking at. So we're going to start with talking about detecting coherence across 2 communication streams, discuss how we can extend coherence to more than 2 data streams and the difficulties that involves, and we're also going to talk about how wavelet coherence can handle non-stationary data. And so all these terms, if you're not familiar with them, will become familiar as I move through the talk. Okay, so I'm going to start off with an introduction to spectral analysis. And I'm going to do it from a time series perspective, because this is the traditional setting in which spectral methods have been developed, and this is a very rich and well understood area. Now, what I'm going to be doing later is I'm going to be applying these ideas to point processes, which is not as standard as in time series, but I think these ideas are best introduced in a time series setting. So let's just move away from cybersecurity for a second, and what we're going to be doing is we're going to be considering ordinary time series. And when I mean ordinary time series, I mean some random process in discrete time that is some regularly spaced sampling of an underlying continuous time process. So you're observing some underlying random process at regular sample points. So, whenever you're taking a temperature reading or a wind speed reading or, a seismology reading, you're taking a sample at particular times. The second order stationary process is defined as a random process which has constant mean, and that the autocovariance sequence, so that is the covariance between the random variable at time t and the random variable at time t plus tau, some lag tau either in the past or in the future, is independent of your global time parameter t and depends only on the lag tau. So it doesn't matter where you look in the process, whereabouts you are in terms of global time, your t, the covariance between that random variable and what's happening at tau in the future is the same no matter where you are. Okay, so this is the second order stationary property. If that's already ringing alarm bells with you, good, because they're supposed to, and that's where wavelets will come in later in the talk. And then what we can also define is we can define two jointly stationary processes. So if we have two processes, two different time series, then you're taking observations at the same time points, but they are of different things. Then we have x1 t, x2 t, and we can also define a cross-covariance sequence, which is the covariance between x1 t and x2 at t plus tau, and we say that these processes are jointly stationary if that guy there only depends on the lag tau and doesn't depend on the global time parameter t. Okay, now you could analyze time series in the time domain. You could look at trying estimating these autocorrelation functions. That's not necessarily a good idea to do, and the reason being is that autocorrelation and cross-correlation functions are notoriously difficult to estimate. Invariably you're only really going to get, a finite length, one realization of finite length of your time series, and you need a way of estimating that autocorrelation structure from that. Now, doing that with a finite length observation is particularly challenging for large values of tau, because if you have small values of tau, then you have lots of points where you can estimate what it's doing one step ahead of you. But if you only have a time series of length 1,000 and you want to estimate what's happening 400 in front of you, there's only there's a fewer number of pairs in which you can use to estimate that. And when you get tau bigger than n, then that becomes even more troublesome, and you have to then start thinking about parametric models and fitting. And the statistical properties of your estimator of the covariance, the autocovariance function or the cross-covariance function are very difficult to interpret. They can quickly become intractable. The distribution is unknown, and particularly if the processes have their own internal structure, i.e., in the case of time series are white, or if they have internal structure, i.e. they're not uncorrelated, which in time series would be white, and in the point process setting would be Poisson, which are cases which we don't want to be dealing with because we feel as though those are bad models for our data. And therefore, given these problems, it's very difficult to devise statistical tests. So that's where spectral methods come in. So second order stationary processes, they have a very elegant and natural frequency interpretation. And that comes from the spectral representation theorem, which was done by Cramer, one of the many, many things that Cramer has contributed to the world of maths and statistics. And essentially it says that any random process xt can be considered to be an infinite sum, so this integral here, of oscillating sinusoids, or complex sinusoids, which is given by these e to the I minus e to the I 2 pi ft, which have random amplitudes and phases, which is given by this guy here. These guys here are this is our waves, okay, and they have waves of all different frequencies between -0.5 and 0.5. This is with a unit sampling length. In the situation where you have a non-unit sampling length, this changes, but I've just kept it for a unit sampling length. This is essentially what you might know as the Nyquist frequencies, and then every realization, you have a new kind of a realization of these random amplitudes and phases, which is given by these guys here. But the expected, these are uncorrelated with one another at different frequencies, and at the same frequency, the expected value of this guy here, which is the variance, is given by this function SFDF. And this is our spectral density function. And so what the spectral density function describes is the contribution that oscillations at a particular frequency are making to the overall variance and power of the process. And so you can decompose the variance of your time series into different frequencies, oscillations at different frequencies, and the value of the spectral density function at that particular frequency tells you how much contribution oscillations at that particular frequency are making to the overall variance of your process. The spectral density function is fixed, it's inbuilt into the stochastic framework of a random process. Whenever you see a new realization of the same random process, the underlying spectral density function for that process is the same. And a nice thing about it is, and intuitively, is that the spectral density function is the Fourier transform of the autocovariance sequence. So it's taking the autocovariance sequence and the properties that have, which tells you, how the internal covariance structure of your process is working, and it converts that into the frequency domain. And so often what we want to do is we want to try and estimate this spectral density function from a finite length realization of the process, and I'll come on to that in a little bit. So here's some examples. Here's a white noise process. A white noise process is uncorrelated at every single lag tau. Obviously, at tau equals 0, you just have the variance of the process, but you have 0 autocorrelation at all other forward or backward lags tau. And if you take the Fourier transform of this sigma squared times the delta function, then what you end up with is a flat spectral density function, sigma squared. In this case, sigma squared is 1, and so you have a flat spectral density function, hence why it's called a white noise process, because white light has every single frequency in the light spectrum in it, which is why it's white, and that's why a white noise process is called white, because it has every single frequency in the spectrum contributing to it. Here's an autoregressive process. This has a different spectral density function, and this is a frequency domain representation of the internal correlation structure within the process. And the reason why we're going to be using this will become apparent. We can also define a cross-spectral density function. So if we have two random processes, x1 and xt, then there will be, these are jointly stationary, there will be an auto covariance or autocorrelation function. Sorry, autocovariance in this particular case is what I've got here. And then you can take the Fourier transform of this guy here and get the cross spectral density function. And this exposes frequencies which are correlated between two processes. Okay, well, essentially what we have now then is you can describe, if you have a pair of processes, x1 and x2, then you can put those spectral density functions into a single matrix. So you have the spectral density function for process 1, the spectral density function for process 2, and then the cross-spectral density functions. Okay, this has all the properties of a covariance matrix, so it's symmetric. Well, actually, these two things are complex, and they are complex conjugates of one another. So it is, it's symmetric under complex conjugation, and it's positive definite, which means that you can therefore think about how you could define a correlation coefficient between x1 and x2 in the frequency domain. And so you define a correlation coefficient in the usual way, but because this is complex valued, actually what you do is you take the absolute value squared of that to turn it into a real number, and that now turns it into a number between 0 and 1, and this is what this coherence function is. So it decomposes correlation in two processes over frequency. It gives you a frequency domain representation of the correlation between two random processes. And this is a number between 0 and 1. 0 indicating zero correlation between these two random processes, 1 indicating perfect correlation, either positive or negative correlation. You know, this is an absolute value squared here. So it's only between 0 and 1. And this is at particular frequencies. So you can start now seeing what frequencies, if you have two random processes, are they correlated at. And again, what we want to do typically is you might have some finite length realizations of these guys, and we want to attempt to estimate coherence from a single realization of these processes. And this is of vast interest in science and engineering disciplines. Its big breakthrough was in 1990 in this paper here, coherence established between atmospheric carbon dioxide and global temperature in Nature. And this was one of the very first papers to establish that there was a correlation between CO2 levels, atmospheric CO2 levels, and global temperature. Okay, so this is this was the big breakthrough for coherence. And this guy Thompson did a lot of the work. Who was at Bell Labs, did a lot of the work on how you go about estimating coherence, which is what I'm going to come on to now. So how do you go about estimating coherence? To estimate coherence, you need to get an estimator for your cross-spectral density function, and you need to get an estimator for your two spectral density functions for x1 and x2. And ideally what you want is these estimators of your spectral density functions and of your coherence to have tractable statistical properties so that you can then do things like confidence intervals and hypothesis testing and such. So therefore, we need to know the distribution of the properties of the estimator of coherence. Okay, so how do you go about estimating spectral density functions? This, again, is a very rich area of statistical research, and then there's many tools available. It does take a little bit of care in doing it, and people who are not expert in estimating spectral density functions can come a cropper pretty quickly. But typically, the processes involved is to take a Fourier transform of the data, turn it into the frequency domain. That's called a periodogram. And then what you want to do is you want to follow that by doing some kind of smoothing operation. And the smoothing operation, which I'll discuss now, is something called multi-tapering. And this is the periodogram. Here is the underlying true spectral density function. This is the periodogram. This is if I do a multi-taper spectral estimator. As you can see now, the improved statistical properties of what multi-tapering gives. So I will quickly discuss multi-tapering. So essentially, one thing you really want to do when you take a Fourier transform of your data is you want to apply some tapering function to it. Suppose you have, this is your time series. Okay, what you typically want to do is you want to pre-multiply this by a tapering window. Okay, which might look something like that. And then you take the Fourier transform that. The reason being is that if the taper is called HT, then the expected value of your estimator for your spectral density function is the Fourier transform of your taper convolved with the true underlying spectral density function. And therefore, this convolution here, if this convolution gives you something nasty out the other side, you're going to get something which is extremely unbiased as your estimator for the spectral density function. Therefore, if you just take the straight periodogram, where you just take the Fourier transform of your data without doing any tapering, that's equivalent for your taper of just being a box function like that. And the Fourier transform of a box function is something called Fedget's kernel, which is a horrendous thing like that. And so when you take the true underlying spectral density function, you convolve it with this guy, it spreads all the information out, okay? And you end up getting an extremely biased estimator of your spectral density function. What you want is you want to choose a taper like this, which has a nice you want something which is as close to a delta function as possible, because the perfect reconstruction here would be if this guy here is a delta function, you would exactly get an unbiased estimator. So you want a taper which, when you take the Fourier transform of that taper, gives you something which is very narrow and very peaked. And so that's typically why you do tapering. What multi-tapering is, if I just rub this guy out here, multi-tapering is using multiple tapers So the first taper you would use would be, for example, this guy here. Then the next taper you would use would be another taper like that, which is orthogonal to this taper. And then you choose another taper, which is orthogonal to that taper, and so on. And so you might typically use, say, 10, 15, 20 orthogonal tapers and do your tapered Fourier transform. And what that gives you out the other side would be 10 or 15 approximately uncorrelated estimates of your spectral density function. And then you can average through those to really reduce the variance of your estimator, which is exactly what's gone on here. There's been 10 tapers used on this, which are all approximately, which they're all exactly orthogonal to one another, which gives you approximately uncorrelated estimates of your 10 estimates of your spectral density function, which you then average through to get a nice reduced variance estimator, which will also have good bias properties because you've chosen these tapers, and this is the work which Thomson did, are chosen in such a way that the frequency domain versions of these tapers are extremely tight. They're optimally tight. And in fact, to fit something, he said, right, if you want to get a function here which frequency domain is optimally tight inside a certain bandwidth, it just so happens that the first one is the one which is optimal. The second best one is orthogonal to the first one, and the third best one is orthogonal to the other two. So it's a really nice property. They're called the DPSS tapers, discrete Prolux Friedel sequences, and they're great for doing this kind of spectral density estimation. So, you know, if you're a case of your 10 or 15 or 20 tapers, you take the tapered Fourier transform, and then if you want to get the cross spectral density estimator, you just take the Fourier transform of series I and times it by the Fourier transform complex conjugated to series J. If you want the spectral density functions of 1 or 2, then I or J would be equal to each other in this thing. And then you can build up your estimator of the entire spectral density matrix. And it can be shown that for a single taper, this is Wishart distributed. And therefore, if you have multiple tapers and you take an average for your multiple tapers, then it can be shown that that is Wishart distributed with k degrees of freedom, where you've chosen k tapers, and scale matrix S over F. And therefore, you have an approximately unbiased estimator with certain reduced variance properties. And then if you take your coherence estimator is going to be the absolute value squared of the off diagonal divided by the two diagonal terms, and a guy called Goodman decided that he wanted to try and figure out what the distribution of that thing is, if your thing's Wishart, and you know, if somebody spent that much time doing such a horrible, horrible calculation, he deserves to have that distribution named after him. So that is called the Goodman distribution. But it's of known form, it's of closed form, and so therefore it's very useful. And therefore, so this is why is the spectral representation of correlation structure useful? Well, you can have nice physical interpretations of things. You know, if you see peaks at certain frequencies, that gives you a real indication of some underlying kind of driving mechanism within your stochastic process. And this will be especially true when we start looking at point processes in a second. The Fourier transform turns even non-Gaussian data Gaussian. And that's because your Fourier transform is essentially a sum over all your points and the complex with the complex sinusoids in there, and through some central limit theorem, some quite complex central limit theorem arguments, you can therefore show that you can actually get your estimator of your spectral density function comes out being Gaussian. So that's a really nice property, is that it turns non-Gaussian data Gaussian. The other thing is it compacts infinitely supported time onto the frequency domain. So you basically compact everything down onto minus a half and a half, or the minus Nyquist frequency up to the Nyquist frequency. And the other thing is, when you do this, you invariably do it through the FFT algorithm, which is, okay, I'll come on to that a little bit later, but the benefits of that, and that's speed. But what you do is, with the FFT algorithm is you just let it do its thing, and it outputs you can only ever estimate it at a finite discrete set of frequencies. You can't estimate it on the continuous real line, obviously. But the finite set of the frequencies which the FFT spews out at you are what are called the Fourier frequencies. And actually, your spectral density functions at the Fourier frequencies, all adjacent Fourier frequencies, are approximately independent. Yet again, is very, very useful when you come to doing hypothesis testing. And so therefore, these ideas lends itself to statistical analysis, confidence intervals, hypothesis testing, etc. So here's an example. Suppose we have two random processes and we want to test a null hypothesis that the coherence is 0 for all frequencies. And therefore, these processes are completely are correlated with one another. As I say, you end up computing this guy here, your estimator of the coherence on the discrete set of Fourier frequencies, meaning you have L independent multiple tests of H0 across your L Fourier frequencies. And there's something called a step-down procedure, which you can use in this setting, which controls the family-wise error rate to test H0. And this is if you didn't do that multiple hypothesis test correction, you would end up, rejecting the null when you shouldn't do on 5% of your time, which means that you'll be rejecting the null in situations where you shouldn't be rejecting the null. But this is with your corrected value, or your multiple for your to control your family-wise error rate. And now you're only rejecting the null at these frequencies. And I'll come on to this particular spectrum a little bit later, but you can see you have some really striking trends in this spectrum, some very prominent frequencies at which you can start reasoning about the correlation structure between these two random processes.
Sorry, Ed,
Yeah.
you go back just a second?
Sure.
So there's two processes here, right?
Yeah, and this is the coherence between them.
Right. Oh, okay. And so they're sort of convolved down here at the bottom.
So yeah.
High coherent. Okay.
Yeah, so this is coherence at all the different frequencies. Okay. And this is essentially your critical value for this hypothesis test, and therefore you're rejecting your null at these, which is very clear. But if you didn't do this you didn't take care of the fact that this is a multiple hypothesis test, you would be rejecting at all these points here as well, but you'd be incorrectly rejecting the null hypothesis at those because you haven't really taken care of your multiple hypothesis testing. Okay, so that's a crash course in spectral analysis for time series. Now we're going to move on to how you can use spectral analysis in point processes and therefore use it in net flow data. Okay, so I'm going to represent a point process by nt, and what n is it's the number of events which have occurred at time t. Okay, so this is a random, non-negative integer, and at time 0, you have 0 events having happened, and then you have an event, this becomes 1, you have another event, this becomes 2, then 3, etc. And so what you can think of in this setting is these are net flow events on an edge between two nodes in your network. Okay, you have a net flow, a net flow, a net flow, and this is just counting how many net flows you have between device A and B on your network. Okay, so suppose we have two point processes. These are two event processes on two different edges. Now, you look at these, okay? What does it mean? Each one of these lines corresponds to an event. What does it mean for these two things to be correlated? Okay, that's an important question. And obviously you can't get any idea about correlation out by just looking at these event processes. So, what does correlation between these two things mean? And how would you go about answering the question, are these two processes correlated? And if so, how can we characterize that correlation? Okay, what does it mean for them to be correlated? So to do this, I'm going to have to introduce a few different definitions. We're going to have to introduce the differential increment, which is essentially it's the change in your counting function, and we're going to be dealing with simple ordered processes. So this either takes a value of 0 or of 1. So I either haven't had an event at t, which means that this is 0, or I have had an event at t, which means that this is 1. I can't have two events at t. And therefore you can define, so the first order property of a point process is given by its intensity, and this can be thought of as the instantaneous rate at which events are happening. So it's just a kind of a density, an instantaneous density of events. So what is the expected value that I have an event at t divided by dt? And then I can also define the second order properties through the second order intensity function. And this is now giving me some indication about covariance between these. Okay, I'm not quite at covariance yet because I haven't subtracted the means, but this is looking at the interaction but the interaction term of your covariance. And so this is kind of asking the question is, if I'm here, and how is me having an event here or not having an event here correlated with there being an event at some point in the future in either of the processes? Okay, so it's looking at the interaction. I have it. Is there a correlation between me having an event here or not having an event here with my own process having an event in the future or not having an event in the future, or with the other process having an event or not having an event? So you can characterize. You can either have the cross second order intensity if I and j are different, or you can have the auto second order intensity if I and j are the same. So that would be looking at the covariance of the process, the internal covariance structure of a process, or the cross covariance structure of a process. And again, we can use the same ideas that we can have in time series. We say that a point process is second order stationary if its intensity function, the rate at which events are happening, is constant in time, and that this auto intensity function is dependent only on the time separation between t and s. So it's only dependent on the lag tau. It's an analogous definition of second order stationarity to time series. Now we can move on to defining, this really is covariance intensity, because now I've subtracted the means off here. I've got this interaction term. What is the expected value of having an event here and having an event in the future, minus the expected value of me having an event times the expected value of me having an event in the future. And I can do that either between two processes, I and j, or if I and j are the same, that would be the auto covariance of this process. And then also, this is for two different time points. T and S are different here. You just have to take a little bit of care when you have T and S are the same, because naturally, if you're, say you have a single process, you are going to be correlated with you having an event here and you having an event here. Okay? So, that happens. So that's what this guy here is just doing there, is it's just taking care with that delta function, so it's just picking that out at tau equals 0 of what happens at the zero lag. And then I can do the same thing. So now I can define a spectral density function of a point process, or the cross-spectral density function of 2 point processes, by taking the Fourier transform of this auto-covariance sequence or cross-covariance sequence, or intensity function. So that's just defined in the same way. And again, I can define coherence in the same way. And significant values of coherence tell us frequencies are harmonics at which correlation is occurring in our two processes. And I'll try and emphasize this in a little second with an example. Now, the other cool thing, and this is cool, is that the phase, this guy here, your cross-spectral density function, is complex valued. The phase of that complex, the argument of that complex valued function tells you information about delay in the correlation. So suppose you have, what's the next slide? I'll talk about it a little bit later as well, but suppose you have two independent homogeneous Poisson processes, but buried inside those homogeneous Poisson processes is some kind of periodic signal, a ping, 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 ping. And then in the second one, that's also happening, but it's happening at a delay. Then your coherence function would pick up the frequency at which the pings are happening, so ping, 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 but the delay between it happening here and happening here in the second process will be picked up by the complex argument of this guy. And so you can get delay information out from spectral density functions. Unfortunately, I don't really have time to go too much into that, but if anyone wants to talk to me more about how you can exploit these things for estimating delay in correlation, then I'll be happy to talk about that. Okay, so how do you go about estimating these guys? You can do it in the same way, and you can do it using a multi-tapering technique, as I talked about here. Now, this is where things are slightly different. Point processes have the advantage that you can actually represent them in continuous time, because you still only have a finite number of events which have occurred. So you can do a continuous time formulation for the spectral density function, or you can use a discrete time formulation for your point processes. And this discrete time formulation, it's not a sampling, it's a binning. So it's how many events did I have between 0 and 1 unit time, and between 1 and 2 unit times, between 2 and 3, the counts. How many counts of net flow did I have in those bins? So you can use this, and that's probably more commonly what is found in practice, is you get an idea of the number of events which have happened in discrete bins. But if you actually know the exact time which the events occurred, you can do a continuous time formulation of that as well. And they have their own benefits and disadvantages, but this is just emphasizing that you can, with the discrete time formulation, you can use a taper in the same way. You can also have continuous time representations of these tapers, and so you can do multi-tapering in the continuous time setting as well. And again, you know, this is a paper we've got with my postdoc in preparation at the moment, but you can again derive the distribution for these guys. They're Wishart distributed. You know the number of degrees of freedom, and you can get this in continuous time and discrete time. I've just emphasized this here, is that by binning data, you're naturally losing information. Okay, so if you have a continuous time point process and you decide to bin it up into little time segments, so you've got how many events I had in this interval and this interval and this interval, you are losing information. You're blurring your data. Okay, and that's an irreversible step, and that irreversible step manifests itself as some mutation of your spectral density function. You get some kind of loss in information in your spectral density function. Things kind of bleed a little bit in your spectral density function. So it's not quite the actual true spectral density function, which is up here. And then our paper, which we've got in preparation at the moment, talks about the effect which binning your data has and that loss of information, how that manifests itself in the spectral density function. Okay, so let's look at an example. And this is the example which I was just talking about. We have a process, one, which is a regular pulse at a rate omega per second, and that's submerged in a homogeneous Poisson process. So you have a homogeneous Poisson process, and then inside that you just have this ping going on at a regular frequency of omega. And if you wanted, you can sit by hand and work out what the auto covariance for that particular process is. This is the Poisson part of it, and then this is the pings going on. And then you can take the Fourier transform of that, and you can get the spectral density function. You have a flat line, which is the part for the Poisson process, and then you have these kind of delta functions, which are at the frequencies at which this ping is happening. And process 2 is the same regular pulse, but with a delay q. So it's also going at the same frequency, but there's just a little bit of delay in when it's happening. And that's submerged in an independent Poisson process to your first process. That's actually these two processes here, okay? So suppose you want to look for that behavior. You can calculate the coherence function. It should look something like this. However, you want to estimate it. This is estimated from single realizations. You have two single realizations of those processes, and you can see very strikingly how it's picking out the correlation in that kind of regular pulse. Okay, really clearly, and it is picking out exactly the right frequencies. So you can go from this, which is completely kind of really difficult to understand what's going on in terms of correlation inside these two things, and then just by looking at the spectrum and converting it into the cross-spectral density functions, the spectral density functions, looking at the coherence, which looks at the correlation between these two processes, you can see the striking correlation occurring, and then this kind of noise at the bottom is all the zero correlation, essentially, which is the independent Poisson part of that. And then if you work out the phase at each of these peaks and take the average of them, you can get an estimate for that delay as well, and you get a really good estimate for that delay, which is happening. So these are kind of contrived toy examples, but you can get a real flavour of how this is a proper hypothesis test, because this is all happening at Fourier frequencies, so these are all independent of one another.
Sorry,
yeah.
Just make sure I have this. Maybe a dumb question, but does this mean that we have this point process that is Poisson, and then we have this every tenth of a second,
Yeah.
we have a periodic signal. Is that right?
Yep, that's
Okay.
exactly right. Yep.
Right,
And in the two channels, you have the Poisson processes are independent. So you've got this independent Poisson going on,
Okay.
and then but there is like this kind of ping, 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 which is present in both of them, but with a delay.
Right. And
that's
the
the
reason we have
frequencies.
coherence at every tenth of a second is because of harmonics.
Yeah, exactly. So you are correlated with what's happening in you're correlated with what's happening with you in point one. So that's equivalent to 10 seconds actually in the future.
Okay.
But you're also what's happening 20 seconds and what's happening in 30 seconds because it's happening. So that's what's picking these guys out as well. Okay. So let's apply this to some real data. This is the LANL data set. And I'm not necessarily saying I'm doing anything amazing or seeing anything amazing here, but we just apply these very simple techniques to this data set. And so what this is the graph of messaging channels under analysis. And so we've basically picked out about 500-ish device triples, ABC triples, and looked at correlating the net flow between those three, on the two edges between those three devices, so A to B and B to C. And this is just a representation of all the triples which were going on, which we used. The weight, so the size of the text and the node are kind of respectively proportional to the number of ingoing and outgoing edges into that particular device. The weight of the edges and color is proportional to the intensity or the rate of the net flow on that particular edge. Okay, so there's arrows going. You see this guy here, C5721, I guess is a server of some kind.
I think it's the Active Directory.
Okay.
So pretty important machine.
Okay.
Yeah.
And so if I just took one of those, obviously just by random, took one and looked at the coherence. So this is 3 devices, 2 edges, I think going through that central node there, and looked at the correlation structure between the net flow data on those 2 edges. Now, this is why some care is needed with a little bit of expertise in spectral analysis. If I did 5 multiple tapers, when I was doing my multiple tapers over here, you get something which is pretty noisy, but these are big data sets. You have a lot of points in them. So that the bigger the data set, the more tapers you can get away with, and the more tapers you can get away with, the lower you can get the variance down because you're doing more averaging. And if you use 40 tapers, you get this guy here out. So the blue here is the blue and red lines respectively illustrate the actual spectral, sorry, that was a typo there, the actual spectral. So this is, I have an A, B, C. So this is the spectral density function for the net flow on the AB channel. And this is the spectral density function for the net flow on the BC channel. And this gray here is the coherence. So what you can see is this to me is indicating there's some kind of broad correlation structure between these two things. It looks like it has the signature of a Hawkes process, which is a self-exciting or a multivariate one, so a mutually exciting processes. Looks at this kind of behavior down here as kind of indicative of mutually exciting behavior in spectra, but then you see this quite pronounced regular periodic signal. And here is if I took, so this is taking all the significant values of coherence. The red is where I've got significant values of coherence. So here I've got, this is significant, this low-level correlation structure, this broad kind of correlation, low-frequency correlation, this kind of more, general correlation which is going on between the processes. But then you have this periodic signaling, which is being shown up quite nicely in these channels. And that is at a period of 0.0017 hertz, and that is pretty much exactly 10 minutes. Do you know what that could be? Dropbox?
Yeah, I mean, it could be some application layer sort of periodic thing.
But the point is, I guess the point being is that if this is normal behavior, you should learn this, okay? I can now see normal behavior on my edges, okay? I expect this. And then if you suddenly see something which isn't like this, then, you can start investigating further. But, mainly as a tool of characterizing, I'm trying to sell this more as a tool of characterizing your network and trying to understand really what the correlation is on your edges and giving some feel for what the correlation is on your edges rather than kind of using it as a tool to detect anything at the moment. And then if I clustered, this is just playing around with the data essentially. If I clustered these into using a Gaussian mixture model on my coherence functions, I cluster these into approximately 4 different sets. And here, 325 of the 500 odd triples of devices, essentially 0 correlation in them. And then on the others, you've always got this 10-minute, seems to always have this 10-minute thing going on. 85 of them, that's the only thing which is going on those triples. And on 29 and 61, so 90 of them, there is some kind of other correlation going on. There's quite a lot of correlation going on these 29 devices. So, this is just a way of kind of getting a feel of what kind of edges are behaving, in a similar way.
It's just surprising. There's a lot more correlation than I would expect.
Okay.
Actually, that's I think significant.
Okay. So again, this paper here, which is the conference paper, we just have accepted, which is just kind of playing around with these ideas on the Lanel data. Okay, so in the remaining time, I want to talk about 2 things, and that's how do we scale this up? So I've just been talking about 2 edges and how you can look for correlations on 2 edges. How do we move to 3 edges, to 4 edges, etc.? So we might have 4 devices and 3 channels, A to B, B to C, and B to D, or A to B to C to D. And we want to try and capture all the correlation structure which is going on in here. And so how do you go about scaling this up to more than 2 dimensions? Well, we're going to have to consider something called partial coherence, and this is a frequency domain analogy of partial correlation. So partial correlation is important because if you don't have partial correlation, you end up with things like someone's intelligence is correlated with the size of their feet. That's true, but that's because the correlation is happening through age. Okay, and if you condition on age, then there is no correlation between the size of someone's feet and how intelligent they are. So this is why partial correlation and partial coherence is important, because if you have direct, so both of these things, there is, in this situation, there is, say you have 3 random variables, there is direct association with these, and there isn't direct association with these. In both of these situations, if you didn't condition on 2, you would get correlation in here, because the correlation would happen through this channel here. So it's important to think of partial coherence as the frequency domain analogy of partial correlation as a way of controlling for this indirect correlation which might happen between 1 and 3. And this has been, in time series analysis, this has been used a lot in analyzing EEG, I think it's EEG, yes. ECG, EEG is the heart, isn't it? Thank you, ECG. ECG, which is when you put a load of probes on someone's head and you read the brain waves coming out. And this has been used, in this paper it was used on schizophrenic patients for understanding which of these, so you're getting a time series on each of these nodes, time series on that one, time series on that one, and trying to understand the kind of internal coherence structure, correlation structure of how different parts of the brain are working in schizophrenic patients compared to non-schizophrenic patients. So, I'm going to talk about how you can do that in this setting as well. And so now we can consider the partial coherence function. So this is coherence between signal J and signal K after I remove the linear effects from the remaining processes. Okay, so it's kind of taking control of these kind of situations here. So in this situation, you might go, right, I want to consider what is the coherence if I have a time series occurring here, or a signal occurring on here, and a signal occurring here, and a signal occurring here. What is the coherence between 1 and 3, J be 1, K equals 3, when I condition on 2? Okay? And in this situation, you should find that you would still find correlation there, even when you condition on 2, because you have a direct association between these 2 things. But in this one, you'd hope that you wouldn't, that would kind of control for that, and that you wouldn't end up seeing any coherence between 1 and 3 in that situation. Okay, so how might we look at this for a three-process model in this situation? We have three devices now, but now, in many ways, this is now converting edges between devices to the vertices on the graph. Okay, so now I have a point process here, a point process here, and a point process here. So you can just map that onto here. And I want to understand the correlation structure between these three point processes, net flow processes between these devices. And so the simple model which I'm going to use to demonstrate that how you can use this is on model AB. I've got a homogeneous, between A and B, I've got a homogeneous Poisson process and a periodic signal. In B and C, I've got an independent Poisson process to this one, and I'm taking this periodic signal and I'm Bernoulli trialing it. Okay, so only some of those periodic signals, those pings, will actually end up going from B to C, and I'm putting a Bernoulli trial on which one of those goes from B to C. And the same here, I've got an independent Poisson process to this Poisson process and this Poisson process, and I'm Bernoulli trialing the pings which are coming from A to B into D, and this is an independent Bernoulli trialing. Okay, this again, very toy example. Okay, but the reason I wanted to do this is because partial coherence has never been understood in the point process setting before. It's not even, people haven't even wondered whether this is a thing in point processes. Okay, so this is a project I did with my MSc student, my master's student, graduate student, this year, and we looked to see if we could actually show that partial coherence is a genuine thing in point processes, and can we detect it? And so the model she came up with was this model. Okay, which is quite a clever little model to do it, because what we should find is that, okay, you're getting association between here and here because of the pings. All right, only some of them are going from B to C, but there's still some of what's going from A to B. And you should get association between A and B and D because the same thing's happening here, but you shouldn't get any association between those two guys here because the Bernoulli trial on each one of these is independent. And what you should find is if you just use coherence, you should claim that there's correlation between these two processes. But if you use partial coherence, you should claim that there's not correlation between these two processes. And that's exactly what we found with these guys here. So this is the coherence between A, B, and B, C, the coherence between A, B, and B, D. Yes, this is what is expected. This is the coherence between B, C, and B, D. So these two guys here, these two net flow, for example, data sets, and we are picking up, an erroneous coherence here. We shouldn't be really picking this up because that's through an indirect channel. But when we look at partial coherence, yes, we're still getting coherence. We're getting significant values of coherence here, but actually once we look at partial coherence between BC and BD, we're not rejecting the null hypothesis anywhere. So this is the first demonstration that actually partial coherence is a thing in point processes and that you can use it correct and it can show the things you expect it to show. So, yeah.
First, that your power the height of the coherence is reduced in partial.
Yes, that's true. That is true.
Less significant.
Yes, yeah, still significant, but less significant. Yeah.
Can you talk about why?
I have thought about why this is. You're still only estimating it from a single realization of these point processes. So you're not going to do it perfectly. And you can see you still pick up a kind of trace there of it as well. So obviously you can't, with a single realization, I don't think you can really completely get rid of that underlying effect, but you can get rid of it enough such that you don't reject anymore. So yeah, it's interesting. I've noticed that as well. You're reducing here, and you're just about getting away with it, really. But you are getting away with it. So it is showing that partial coherence is a genuine thing in the point process setting, and you can see why this is an important thing to do, is try and understand correlation between edges on a network. So yeah, this is my master's student project, a really nice project, and she's doing a PhD with me next year, which is cool. So we're going to be looking at extending these ideas to more than 3 edges. How can we scale this up onto larger networks and start really understanding partial coherence across multiple edges? How do you go about doing that? And there are troubles with this. Okay, so to get this partial coherence function here, you're having to take the inverse of the spectral matrix. And you're essentially taking the precision, the spectral precision And that's how you can end up calculating your partial coherence. Now, obviously, if the dimensionality of your number of processes, the number of processes you have, point processes you have, i.e. the number of edges in which you're analyzing on your network, gets close to the number of degrees of freedom in your Wishart distribution, okay? And that is the number of tapers you're using. So here we were getting away with 40, okay? But as the number of processes you get starts approaching 40, the number of edges you're looking at, your spectral matrix here becomes more and more ill-conditioned until the point at which you reach equality, and then it becomes singular. So the closer you get to that degrees of freedom, the nastier this spectral matrix becomes, the more ill-conditioned it becomes, the worse the estimate becomes, and that means that when you take the inverse of it, it can cause all kind of havoc. So how you go about kind of, taking care of this dimensionality problem and scaling this up is an open issue, although it has been tackled a lot in time series analysis, so there's a lot of ideas which can be borrowed from there and using kind of shrinkage techniques. When you shrink your spectral matrix towards the identity matrix, you can condition your matrix in a nicer way. And again, right, so the big thing, stationarity is a bold and completely wrong assumption, is all I've shown you is stationary stuff. So that's what I just want to finish up the last 10 minutes in this talk, is how you can go about tackling non-stationary data. And that's using something called a wavelet. And a wavelet is, if you don't know what wavelets are, they are very cool. They keep me in a job pretty much, so I like them. And they are a way of doing localized frequency analysis. So you can use wavelets for many different things, and you might know them from kind of doing image analysis or compression or whatever. But the way I'm going to be talking about it is through kind of it's a time frequency approach. And what you can see is so this is a Morley wavelet. You can see, so it's called wavelet, although I spelled wavelet wrong down there. It is wavelet. It is like what piglet is to a pig is wavelet to a wave. It's a small wave. So that's why it's called a wavelet. And what it is like a kind of small sinusoid. And then what you can do is you can slide this sinusoid along to the point in time which you're interested in, and then you can expand this kind of small wave, or you can compress this small wave. If you expand it to something like this, then you start analyzing low frequency structure in your random process. If you compress it to something like this, you're analyzing high frequency structure within your process. And then so your B parameter here is your sliding thing. That's sliding your wavelet to the point B at which you want to do your analysis. And this A parameter here is controlling essentially what frequency you're looking at. Large scales, you're looking at low frequencies, and small scales, really tight things like up here, you're looking at high frequency stuff. And so you can build up now a time frequency map. So when you're just doing the Fourier transform, you're just taking everything and you're correlating with infinitely long sinusoids, and you're just turning that into a spectrum. Now what we're doing is we're looking at little localized sinusoids essentially, and we're converting that into a time frequency map. And so you can again build up. I won't go into too much of the details, but you can do a continuous time or a discrete time wavelet transform of your data, and you can convert that into a wavelet spectrum. And now we have two parameters here. You can think of A as being related to frequency and B being related to time. And again, we can do wavelet coherence. So this is the same thing, but now just looking at coherence in the time frequency domain. And this is something I did a lot of work on with my PhD supervisor, Andrew Walden, and in a series of papers in 2009, 2010, 2011, we did a lot of work on understanding the statistical properties of wavelet coherence estimators in time frequency domain. So now what we're looking at is we're looking at the correlation structure of a random process at a particular localized time B at certain scales. And you can change the scales at which you're looking at, and you can think of scale associated with frequency. So it's just a way of doing time-localized spectral analysis, essentially. What the statistical properties of this is in the point process setting is a current research area of mine, and I have a grant ongoing, and we've got some papers in preparation because the grant's just coming to an end now, but we've really spent a lot of time looking at what wavelet coherence means in a point process setting and the distributions of your coherence estimators and stuff like that. So that's work which I'm doing in my postdoc at the moment. But here's just to finish off some very simple examples demonstrating what you can do. So in this particular example, we have this independent Poisson process and this periodic signaling. But what happens is the periodic signaling changes at a certain point, and it starts getting, what's that, scale. So it's a higher scale, lower frequency. So it goes from high frequency periodic signal. There's a change to a low frequency, and then it goes high frequency again. And you can see this is just from a single realization. Okay, you see you're doing pretty well even with a single realization of your data. You can spot this change, and there was correlation in my two processes at a scale of 0.4, which corresponds to 1 over 0.4 hertz. So you can directly map to frequency. Suddenly there's an abrupt change, which you're picking up here in the correlation structure, and then it's going back to what it was before. That's using a discrete time setting for your point processes, and this using a continuous time setting. This is just taking an average over 100 realizations. So you can see how wavelet coherence is doing a pretty good job at picking out that change in structure and change in correlation in your processes. The key thing here is you're having to take a smoothing operation. If you don't take a smoothing operation here, this thing just becomes 1. Okay? So the smoothing operation is the difficult thing. That's what's taken some time to try and work with. We use smoothing in the time domain, and to get the kind of the statistical properties under that smoothing is what's tricky. But some demonstrations, some toy examples of what you can do with wavelet coherence. And then this is actually analyzing real data. So they sit, this is quite cool, they sit some mice down and they show them videos. And then they have, this is two, essentially they then isolate neurons in their brain, and they can take the firing events from the neurons in their brain. So point process is the firing of two neurons which they isolate. And they show them videos. So I don't know what they're showing them here, Tom and Jerry or something here, and then they relax it back to something else. But what we did is we analyzed these two kind of neural firing point processes using wavelet coherence. And so you can see actually some, this is the wavelet coherence spectrum. So this is time, and then any particular time, if I want to look at a particular scale, I'm kind of understanding the internal correlation structure here. This is just taking the significant values. So anything which is not statistically significant, I set to white here, and anything which is statistically significant still remains here. And you can see this bit here matches up with this bit here matches up with this bit, and then this bit here matches up with this bit. So there is, when this, Tom and Jerry, whatever, they're showing them, when this thing kicks in, this video kicks in here, suddenly these neurons really strongly correlate with one another at quite a key frequency here. Again, this drops out, and it moves back to more something kind of like that, and then when it kicks in again, you really get this correlation structure coming back in again. So this is the scale domain, and this is if I just convert it to the frequency domain. I now have a time frequency map of the correlation structure within my point processes, and again picking out this nice kind of change in structure. I don't know what that means. I'm sure the people who came with the data, I hope are going to be interested by this when I show them the results. But hopefully they'll go, oh, that makes sense. But all I'm doing is I'm showing them this is what these two neurons, they are correlated. There is coherence in there, and it's on these frequencies at which you're getting this structure. Okay, just to conclude. So what I've done is I've introduced spectral methods for point process data. Time series is very well established, but for point processes, not so much. And I've shown how you can detect and characterize correlation between point processes, and essentially net flow on edges. This is really important. This is super fast. Okay, all the stuff even the wavelet stuff I'm doing here, the discrete time wavelet stuff anyway, is just some clever use of the FFT algorithm, the fast Fourier transform. So I can take thousands of events and get spectral estimates and coherence estimates with like that on MATLAB on a laptop. Okay, really, really quick. And so you can get close to doing kind of real-time analysis of understanding correlation structure on edges. So some open questions. How do we go about scaling this up? That's the big thing. How do we go from 2 edges to 3 edges to 4 edges to larger networks and understanding correlation structure? The other thing which I think is quite interesting is also these kind of things here you can treat as images. Okay, in many ways these are images of the correlation structure on a pair of edges. And so why not feed them into convolutional neural nets or something like that? Why not learn what normal behavior looks like, so that then you can, if you throw in another one, you can into your machine learning architecture, it might flag this up as being something which is different to what you've learnt as being normal behavior. So you might look at a pair of edges on lots of days when you know that something, you know these things are fine, and you can get your machine learning architecture to learn all that kind of normal behavior, because they'll look different every day. But then you can use these as images, essentially, and all the machine learning architecture which is available for images. So some acknowledgements. Andrew Walden, who was my PhD supervisor several years ago now, but who the time series work on wavelets, he was my collaborator. Currently, Alex, who is my postdoc, who's done a lot of work on wavelet coherence for point processes. Lee, who is the master student who's coming into moving a PhD. Next year, she did the work on scaling up to partial coherence and showing that partial coherence is a thing in point processes. And we'll be looking at how we can go further with that during her PhD project. To Simon, who gave me the mouse data, and to funding from EPSRC. There's a list of references, and thank you. Any questions? Yeah.
For the Lanol data,
Yeah.
were those directed edges you had ABC?
Yeah.
So those you got the direction of the net flow.
We've got the direction of net flow and those things, yeah.
Right.
So Jordan picked out all the ones which were clean, basically had a lot of net flow between an A to B and a B to C.
Okay.
Yeah. Does that ring alarm bells for you, or
No. Well,
Okay.
it's really important. Otherwise, it could be just two.
Yeah, no,
bolts
yeah,
just
yeah.
pinging to the same.
No. They are three separate devices. So these are the devices here, and the arrows indicate, the A to B, B to C.
Sure thing.
Yeah.
But sometimes it's not always easy to know the direction
Okay.
of depth of it.
Right.
Necessarily.
Okay.
And so if I had two things that were just independently pinging away, would they show as being coherent, or
If the pings were independent of one another,
but if they were just pinging literally every p second, they were pinging, and that one does it every p seconds, would they still show as being coherent?
so the pinging is happening at different frequencies.
No, same
frequency.
They're just pinging.
Yeah, no, it would show they
None
were.
of them cause a relation. They just both happen to be pinging.
Yeah, that would show
That would
correlation.
show correlation
Yeah,
as well.
yeah.
But I guess it's particularly interesting if you have missing pings, and those are missing in both series. Is that
Yeah.
the real point?
Yeah. So again, so you have what you're saying. You have
For Bernoulli trial,
the Bernoulli trial. Yeah.
Yeah.
Yeah. So that's the kind of this model we were doing here, where you have, a ping, and then some of the pings are going this way, some of the pings are going through that edge. Yeah. Then that's exactly what we're showing here, is that if they are independently choosing which ones they take, then through a partial coherence method, you should be able to get rid of those. If they're not independent, you will still end up finding coherence. Yeah.
I got a question.
Sure.
Stationary or non-stationary, really important. I don't think we understand it very well. We, in like our anomaly detection, we have self-updating models because we assume there's non-stationarity.
Yeah.
So we update every time we look at the data, we sort of update the models. And so it would be really nice to understand how necessary that is.
Yeah. Okay.
And so quantifying the level of non-stationarity in some way would be a great contribution.
Okay.
So it's just a suggestion.
Sure.
If you can
As I
tell-
go, there's in time series, there's a huge amount on testing for stationarity.
Okay.
Point process setting, I'm not familiar with there being much in the literature. For testing for homogeneity, yes. If you're assuming Poisson and you want to test homogeneity of your Poisson processes, then yes. And my other PhD student, Yusuf, has got a very nice paper coming out hopefully soon, where he uses wavelets for testing homogeneity at different scales and point processes. So you can look at kind of multi-resolution analysis and understand on what scales these things are inhomogeneous. In terms of, but homogeneity and, as you know, and second order stationary are different things. So yeah, really understanding whether the internal correlation structure changes in time. In a point process setting, I'm not aware. That doesn't mean to say it's not been done. But if that's a useful thing for you, then it would be really good to look
all
at.
this infrastructure to update the models, right?
Yeah.
It's expensive. I mean,
Yeah.
if you do it at scale.
And if we're going to implement wavelet methods on this, you want your wavelet to fit in something which you can approximate as being stationary. That's the key thing, is that your wavelets are fitting in areas which you call locally stationary. And so to get an idea of what is locally stationary gives you an idea of how far you can push your wavelet ideas. Any other questions? Yeah.
These methods apply to automatics kind of events that are happening at regular, precise frequencies. Can we extend these to user behavior signals which are happening at much lower frequencies and not exactly the same frequency?
No, exactly, and I'm really glad you raised that point. What I've shown you here are I've done periodic things because it just makes things look clearer, and I've used it as a demonstration. Okay, but yes, completely. If you have more user, which is not as these are not periodic signals. This is user behavior, but there's correlated user behavior. You should definitely still be able to find that structure using coherence, for sure. And if it's more low frequency stuff, I just used pinging here because it's a useful illustrative examples to use. But yeah, no,
You think that they are not happening at exactly the same time, like not every 8
No, sure, yeah.
1 days. So it shouldn't be a problem.
It shouldn't be a problem at all. So you're talking about some kind of maybe self-exciting or mutually exciting behavior where I do something so they do something, but it's on a more kind of low frequency basis. But it's not happening at regular. Definitely, no, coherence should really look to pull that kind of behavior out. That's a point I want to emphasize. This is not restricted to regular periodic signals. I only use those because they're nice to illustrate things. Any kind of internal correlation structure, coherence can start getting a grasp on. Yeah.
So suppose it's also not related to correlating time series of the same event type. So you could do something like look at network traffic, bytes outflowing, and file reads on the same machine.
Yeah.
Kind of correlate what file, what data is getting potentially exfiltrated.
Yeah. So you're saying with that. So I have to admit, I'm not too clued up on exactly what NetFlow contains, but these could be seen as marked point processes. So the mark is telling you the type of
the volume of
the volume. Or does it tell you the type of event which is occurring? This is
the port will tell you something about that. Yeah.
So if you have a way of filtering these out, then you can essentially get two separate point processes then, and you can start understanding correlation between them. Anything where you have some kind of indicator of them being different types of events that you want to filter into two separate or three separate processes, then you can start just applying these methods as you would do to any other two pairs of point processes. Yeah.
You mentioned this coherence analysis is sensitive to some hyperparameters, and you gave a good example where like the value of L is very important.
Yeah.
Do you have other like hyperparameters? Like,
So
interesting too.
So the value of L. The tapering. Oh, the K, was it? K or L? So here K is your degrees of freedom. So this is the number of tapers you're using. So this is where it takes someone with knowledge in spectral analysis. You have to choose K. If you have short point process, it's short data, you can't get away with a high value of K. The other thing is these tapers. You define these tapers for a bandwidth. So you say, right, I want the tapers which are most concentrated in this bandwidth. The longer data set you have, the tighter you can squeeze that, and so the better tapers you can get, and vice versa. The shorter you have, the looser this needs to be for you to be able to kind of essentially end up getting these distributions. So that is another thing at play, and it does require, actually, I would say it requires some domain knowledge. MATLAB's DPSS function says how long is your process, and then it automatically works out the bandwidth for the optimal bandwidth for you and spews out your your things. But again, you just can't go gun ho into this. It needs a little bit of.
I assume there's some paper telling us optimal things such that which should fit.
Yeah. So if you, again, Andrew Walden, my PhD supervisor. Did I put his? I think I did put his. Yes, this. Percival and Walden, Spectral Analysis of Physical Applications, the Bible of spectral analysis. So this is the one to go to. Anything else?
Excellent. Well, let's thank our speaker, Ed.
Thank you.
Good job.